Hello everyone and welcome to 6th lecture of Digital Elevation Models and Application course. And in this particular lecture we are going to discuss how to assess quality of a digital elevation model. This is very important because as have been mentioning that there are a lot of digital elevation models nowadays available free of cost on net at different spatial resolutions, and therefore before we employ or before we use these digital elevation models, the quality must be assessed. There are different ways of assessing that quality, and while discussing about the spatial resolution, indirectly we have gone through some products derived from digital elevation model and have seen that how the spatial resolution when it varies, how the quality of a product changes. But here especially we will be discussing about how to assess the quality of a specific DEM which we have downloaded for a particular area. Because different digital elevation models which are available have been prepared using altogether different techniques. As you have seen that when we discussed the availability of different digital elevation models, especially those who are available, which are available free of cost, like USGS DEM, which was derived using survey topo sheets, and then interpolations were done, and therefore there were problems about the seams at 1 kilometer resolution and so on and so forth. But when we go for 90 meter resolution SRTM DEM, then what we see is that these are not good for hilly terrain, however they are very good for the plain areas. For example, they are may not be good for a small area of a Himalayan terrain, but they may be good for a flat area of Indo-Gangetic plain. And contrary to this, your Astra DEM may be good for a hilly terrain area because of the technique is different, it is a stereo pair data, and may not be good for plain areas and so on. So these are the issues which are there associated with each types of elevation models which are available, and we will be seeing how to assess the DEM quality. So spatial modeling is often limited due to quality of source data. If the data itself is having poor quality, that means it is having lot of errors, maybe vertical errors, horizontal errors, then the product which we are going to generate using these models, maybe a slope map, aspect map, or maybe a drainage network, or maybe some modeling for flooding or for a dam simulation or other things, then we are going to have problems. So therefore this is very important to assess, and these are the DEM and other data sets are subject to inherent errors. Two types of errors we can classify them. One is inherent errors, which are errors which got incorporated while data or digital elevation was being created, and where are the errors which are operational errors which may erupt while doing the processing, choosing a wrong processing step and not controlling the errors. So inherent errors here will assess the quality of a digital elevation models, whereas operational errors will allow us to assess the quality of a product which has come through a digital elevation model. But understanding about inherent errors is very much required, and that is why in previous lecture I have mentioned that we must go through the metadata which is available through for each type of digital elevation models, which will give us a lot of details about these errors, accuracy part, and spatial resolution and other things. So DEM derivatives are very sensitive to quality of the DEM. If a digital elevation model is having lot of errors, and if you use that DEM to drive a product like slope map or drainage network or any other thing, then the quality may further deteriorate, because these processes at some stage may introduce some more errors. So if the raw product, in this case is digital elevation model itself, is having errors, then these may propagate. So one has to really keep control over these errors. And errors in either remote sensing data or in GIS or a processing steps or in digital elevation model are generally least discussed, and therefore we can mention that these are the errors are still ignored, but these are very, very important because they provide a statement about how accurate the data is or how accurate a particular product which one has generated using a digital elevation model. So that statement or the confidence in our output will completely depend on the quality of a DEM, which also includes the error component. So errors in DEMs are likely to be larger on the shaded slopes, because if I am using the say radar data for SRTM, then that is why I have mentioned earlier that for hilly terrain sometimes we find, especially the hilly rugged terrain like Himalayan terrain, we find that the area which got completely in shadow areas because of oblique angle of radar waves or radar pulses. So we may get errors about elevation values in a shaded slopes. So that is the errors which may there in case of SRTM data. Smooth and featureless terrain. Now this can also come in a optical data, stereo data like Astra DEM. So this one has to take care about this one, that what kind of terrain this DEM is representing, of which area this DEM belongs to, and depending on that we should keep eyes on error component. DEM errors are spatially variable and spatially autocorrelated. That means they keep changing within an area, within a set of or one single file, it may even change. So that one has to remember. Another term which comes while assessing the quality of a digital elevation model is that uncertainty. That is, a model is basically model, when we say digital elevation model or any other model, so it is an abstract form of reality or an approximation of reality, reduced reality. It is not truly a real. That is why spatial resolution is there. So coarser spatial resolution, we have reduced the reality much more. When we are having a finer spatial resolution, we have not reduced reality to that extent and in previous example. But any model, once we use the term model, automatically means it is a reduced reality or approximation or abstract form of reality. And it is basically a downscale representation of the real thing. And as we know, the DEM is also a model of real world features or phenomena which is represented. The phenomena in this case is the terrain or undulations or upheavals which are present, ups and downs on a terrain. And the goal of spatial modeling using digital elevation model is to produce close approximation of reality. That means the product should not represent entirely a different thing than the terrain. For example, if I have derived a slope map, then slope map should look realistic to the real terrain conditions. And if I have not taken care about the quality of DEM or the say Z factor or scale vertical accuracy, horizontal accuracy, then the product may be having lot of errors and may be much more away from this approximation of reality. So whenever, whatever the goal, there may be the lack of knowledge of how good a representation of reality is required. Now again it is depending on our output. As I have been mentioning that if we are covering a very large area, then we go for a maybe a relatively coarser resolution data. And there the representation of reality is much more, approximation of reality or abstract form of reality is much more. So this has to be seen from that scale point of view, and how well a model represents reality. How good we have seen even the same resolution digital elevation model or derived from two different sources, say for example SRTM at 30 meter and GDM at 30 meter. but both are representing the same terrain quite differently, because the way they have been generated, the quality got involved in it, and therefore these models, which one is more accurate to reality of a particular part of the globe is more important. So this has to be also understood very clearly, and how reliable the conclusions are which can be drawn from the model. So if I am using a digital elevation model, example I have been given is, if I have derived the slope map, how close it is to the real conditions of a terrain. So that our confidence or reliability of the product will totally depend about our understanding about the quality of a digital elevation model. And if we lack of this knowledge, can be expressed as uncertainty. So if we don't know much about the quality and error component and other things, then we put them as an uncertainty. So this is how it is expressed as uncertainty. Now this has got, uncertainty has got two components. The first component is about the quality of data, and second is the uncertainty about the quality of processing applied to the data. And earlier I have used two term for errors, inherent errors and operational errors. So the first uncertainty or incorporates the inherent errors, that is the quality of data, and in the second uncertainty, that is the quality of processing, incorporates the operating errors. So these two are important component of uncertainty, and data quality is fundamentally dependent on the degree of errors within a data set. If we are having large errors, then level of confidence goes down, uncertainty increase, and our quality become very poor. But contrary to this, if we are having small error components, then uncertainty is very little, and we get high level of confidence in our data set, and the errors are also very less. And error is the difference between a data set value and the true value. So because in our case is, if we want to really assess the quality of a DM, then we need to have to collect a near true value. Why I am using word near true and why not true value? Because true, for every location it is not possible to collect the true value, because if it would have been possible, then there is no requirement of any model. That means that one-to-one scale, and model is an approximation of reality. So we have reduced the scale, we have reduced the reality. So that is why this is the error will be there in most of the data sets, but how small or large, that is more important here. So the error, if we want to define, is the difference between a data set value and the true value. For example, if a cell in a digital elevation model is showing elevation which is 100 meter above mean sea level, but if the true value, that is on the ground at that particular location, the average aerial average of elevation is 90 meter, then we can say the error component is 10 meter. So that is why it is important here to understand error in this sense, especially related with digital elevation model. And now that the term which we have used earlier in the previous lecture is the accuracy, which is a measure that aggregates or summarizes the errors within the data set. So the accuracy is a statistical statement. Remember this thing. Now generally DM quality is reported in root mean square error or RMSE value, and that variation in error is not communicated by single RMSE value. So that has to be also one single value, because as we have seen that the quality of a digital elevation model varies, especially as well as it is auto correlated. So that is why a single RSME value may not be a true representation of error component in the data. And RMSE value is based on the difference between digital elevation and the elevation at test points measured by field surveys or from existing map or other methods, maybe implying a differential GPS or similar techniques. So, at different locations we may get RMSE differently, because especially these things vary within a data set depending on the terrain conditions. And now when we see this statistics, the visual examination of surface model and statistics summarizes key morphometric characteristics of a DM and can provide valuable additional information about the quality of a digital elevation model. So, statistics, visual examination, these will play very important role while assessing the quality. So, it can be hypothesized that the distribution and scale of errors within a DM are at least partly related to morphometric characteristics of the terrain. So, the features which are present will tell us that how the errors are there, what is the scale of errors, and so on and so forth. An accuracy surface would give a better representation of distribution of error within a DM than a single RMSE value. So, this is equally important in case of a digital elevation model and while assessing the quality. As we know that there is the inherent errors. When we want to assess the quality of a digital elevation model, then we have to assess the inherent errors, and before that we have to see the sources of DM. So, for example, this is not exhaustive list, and the sources of DMs which we will be discussing in a separate lecture, but here just in a very brief for examples we have taken sources of DMs like already available DMs, for example USGS or SRTM or GTM, etc. And maybe we may be having self-made DM driving from contour or point data, or maybe collecting elevation values of point heights using a DGPS or differential GPS technique, and then creating a digital elevation model. So, we will put them all in self categories. If we use ready-made digital elevation models or freely available digital elevation models, then what we need to look into? Then few point elevation data either collected from TopoSeed or GPS. So, if we use these data sets, compare with the real values or the values which are being represented, corresponding values which are being represented in a digital elevation model, then probably we will have an idea about the quality of error component, especially vertical component of a digital elevation model. So, how close it is. But if it is self-made, if we ourselves are made, then we can control these inherent errors in a much better way. So, that then before using all points for interpolation, remove some random points from the source data, and I will explain on this if we are making our, and that example will fits with the this spatial interpolation techniques. So, what we do basically in spatial, what I am suggesting through the quality, how to assess the quality of a DM and how to choose a particular spatial resolution, this spatial interpolation technique, we can devise a very simple method that suppose I am covering an area and in which I am having 100 point heights for which I am having elevation values. These I was supposed to create a digital elevation model implying a particular spatial interpolation technique. But before that, what I can do that I take 10% points, randomly selected points out of this data set initially. So, what I will have here, I am having 100% points. I have randomly selected 10% of points and got and saved it elsewhere for further use. So, now I am having left with 90% of my elevation points for which I will be using for different interpolation techniques. So I can employ different interpolation techniques like maybe IDW, maybe SP-line, or maybe kriging. Now what I will have in this particular example, I will have 3 surfaces. So I will have 3 surfaces using 90% of the data set, one surface of SP-line, one surface of kriging, and one surface of IDW. Now those points which I did not involve in interpolation, the 10% randomly selected points are plotted here. And the corresponding elevation values, 10% points are plotted here. Their corresponding elevation values are checked, how far they were away from these values. And out of, say, in this example, the 3 interpolation techniques I have used. So if I find that IDW values or the surface which has been generated using IDW is giving more close values corresponding to these 10% randomly selected points, then what I will do, in the final step, what I will do, I will take 100% points and directly go for IDW interpolation and can create a surface. So through this process, 2 things I have achieved. One is which interpolation I should employ for my set of data set. So that is the set of data that I can decide based on this exercise, one. And secondly, same time I can also assess that what is the quality of the DM which I am going to generate, because this will, when we will compare these 10% random points with the corresponding cell values, digital elevation values, then I will know exactly what is the error component here. So this, while doing this exercise, we can achieve 2 things. One is which interpolation technique should be employed, one, and secondly, what is the inherent errors which I am going to have with my data set. So this is a rather very quick method. However, one has to remember that for each data set, we have to do this exercise again and again. Because a one particular data set, suppose a data set, instead of elevation values, I may be having a groundwater surface for which I am having observation wells, for which I am having water level data. So for that set, IDW may not be suitable. I may find end of this exercise maybe SP-line more suitable. So for different data sets, different interpolation techniques may be employed, one, and there may be different data quality. So this is what it here means, then, that if we are going for self-made digital elevation model, then we can first perform this exercise, achieve 2 things together, and then go for use the entire 100% data set and generate final digital elevation product. So in this, we will have full control over the quality of the data set. But if we are using ready-made data set, then we don't have much choice. We have to live with that errors, but we must know what are the inherent errors. And how that can be assessed, that we will discuss little later, almost implying the same thing, but the data has to come from some other source. Because if the data is coming from the same source, then it will not reflect about the errors. So we will see little later. So use these data to check accuracy of a DM. These kind of checks or processes can allow us to check the accuracy of a digital elevation. And now this I have already mentioned, that which interpolation techniques for DM is, and this answer will also come from the check or the process which I have already discussed. So DM accuracy may be used to visualize DM quality by showing epsilon bands around contour lines and catchment boundaries. That is also because these boundaries can tell us that how accurate a digital elevation model. This is another way. Stochastic techniques such as Monte Carlo simulation to drive a simple sample of potentially valid model outputs reflecting the influence of DM uncertainty on the modeling processes. So that also can be employed. And quality of a DM can be assessed using GCPs, ground control points or point heights. Here it requires little discussion. And that if I am having a digital elevation model, it's a ready-made digital elevation model, I want to assess the quality of a digital elevation model. And as mentioned just few minutes back, that we need some external source of data, maybe a point elevation data derived from say digital these GPS or differential GPS or maybe some other survey techniques. If that set is available with us, the GCPs, ground control points, on which we have got the high reliability, we feel that they are more accurately collected elevation points, then we can put again, as we did here in this exercise, that those points and check the corresponding elevation of a digital elevation model and how close the elevations of a digital elevation model are coming close to these observations, which are coming either through differential GPS or some other survey techniques. And by which this exercise, this can be done. As I understand that NRSA ISRO India has developed a large library of GCPs. They have collected using differential GPS. So if this large library is made available, then it becomes much easier for any one of us to use those corresponding point heights values derived from differential GPS and then check with the elevation of a different area or parts of India. So because then we can use these library of GCPs as a standard one, assuming that they have while collecting these GCPs they have taken utmost care and maintained the highest quality standards. But unfortunately these are not available, so we have to generate our own or bring from some other source these point heights value. The other source can be a topo sheet, but when we are using a very high, relatively higher spatial resolution digital elevation model and we are using point heights of 50,000 scale topo sheets, sometimes that may not be very appropriate. So here the scale or the source scale of the point heights from a topo sheet will matter most. So one has to take care about this aspect as well. For relatively medium resolution or coarser resolution data and corresponding point heights coming from 50,000 scale may be good, but for higher spatial resolution data and these heights for which the GCPs are coming from 50,000 scale may not be good. So one has to remember. One example here which is shown that I am having a digital elevation models derived from variety of sources here and corresponding point heights are also plotted here. And what we see that when we compare these with the point heights and the corresponding elevation values which are available and then when we compare, then we find difference. So there are different results are shown here against the different point heights. And so what these spot heights derive from topographic map top to bottom here which is of different areas. This is along Kanchenjunga, one set, then this is a Lalitpur area which is a less or very smooth terrain and not much undulations, and then the bottom three images are of Roorkee area which are near flat. So what we see is a highly rugged terrain and less rugged terrain and almost a flat terrain. And when we use the different to assess the quality, then this is how this can be done, that you get the spot height in these three examples. The spot heights have come from these topographic maps, or basically Survey of India 50,000 scale topo sheets. And when we compared, we got different results for different elevation models. So what we here the first one, the first row is the Aster GDM for all three sites. This is the Cartosat DM, and this is the SRTM DM. So three different types of DMs at three different resolutions are here for entirely three different areas representing three different types of terrain. And so as mentioned earlier, depending on the terrain, the errors would be there. It is generally found that for highly rugged terrain, the error component may be little higher, but it also it will depend what is the source of data, how the data has been generated. If it is remote sensing based digital elevation model, then which technique has been employed. But generally, this has been observed that areas of hilly terrain, rugged terrain, we may have large errors as compared to areas which are less rugged or smooth terrain, or completely flat terrain like Indo-Gangetic Plain part of India. So this way we can compare the point heights with corresponding elevation values from digital elevation model, and can have a feeling about the quality of a digital elevation model. So this way we can assess and quantify the errors present, if at all inherent errors, in these ready-made digital elevation models. Now one example we have already discussed earlier, but since this comes here in this reference, that this is a ready-made digital elevation model of 1 kilometer resolution. And if we see very carefully, what we find that we may get some seams present in such type of digital elevation models. When we did not have this SRTM and other digital elevation models at 90 meter, this 1000 meter or 1 kilometer resolution DM was very useful, especially of hilly terrain. But it had the inherent error, that was the seam issue, apart from the interpolation and other errors were there. And another problem came initially when we started using SRTM DM with voids. So voids means no data basically. That means while these images, radar images were collected for snow covered or glaciated areas, no data was collected because of some shadow or some dielectric constant, and therefore these voids, which are represented in this particular example in dark maroon color, that is why the value is very wild, and so that we can declare to the system that whenever it encounters this value, in this particular case the value was assigned minus 32,768 meter. So whenever this value is assigned, this constant value, then consider as no data and do not involve in any calculation whenever this value is encountered within a data file. But later on, employing a simple GIS techniques overlaying, so in the background you are having relatively coarser resolution digital elevation model, for example maybe SRTM 1 kilometer resolution, which was also available, or maybe USGS DM 1 kilometer resolution, and you can pick the relatively coarser resolution digital elevation values from the low resolution digital elevation model for this 90 meter resolution, and you can fill the voids, and this is what the exercise was done. So now you are seeing a completely void free digital elevation model at 90 meter resolution. Now later on, for entire SRTM digital elevation model of this 80% of the globe, the same exercise was done and the voids were removed. But remember that these voids were present in a spatially snow and glaciated part. So and the data, these voids have been filled with relatively coarser spatial resolution cells, and therefore they are suffering from certain types of errors. So, if I employ such digital elevation models where voids have been filled with coarser resolution data, then we have to keep in our mind that whatever the products which we are driving will also have these problems or these errors in inherent errors. But visually sometimes we do not see these errors, but we go, if we zoom it, we may see these errors very clearly. This is a zoom part. So, I am this what we are seeing on the left image is USGS 1 kilometer DEM, and here the seam can be seen very clearly. Why seam is coming? Because two different topo sheets may be of two different scales or may be surveyed in two different years, and when these were mosaic were made, interpolations were done using contours, these seams got developed. And this is inherent error with USGS 1 kilometer DEM. Still these DEMs are being used because for different modelings we may not require a very high resolution, relatively high resolution DEM. So, we may resort to even 1 kilometer resolution. Another example, at the same resolution 1 kilometer resolution SRTM, here we do not see the seam. Luckily in this particular example we do not either seeing any voids as well. But when we see the SRTM 90 meter, which is a void free corrected DEM, then as you can see that compared to USGS DEM, this is highly reliable. Means the quality of DEM is much better than a 1 kilometer USGS DEM or 1 kilometer SRTM. So, there are various ways. Either you can involve the visual inspection, which can give you a quick assessment of the quality of a digital elevation model, zooming it and zooming out at different locations, especially of a hilly terrain, and employing some point heights and then checking the errors, or some statistical methods by which one can do this thing. This is again example of non-void filled digital elevation model of a hilly terrain, and then SRTM void filled DEM. This is Mount Rainier, and two mounts are there, Mount Rainier and Mount Adams are given here, and this is how the after processing the DEMs have been improved. These control points, as I was mentioning, that Carto digital surface model, and these exercise were done using the this GCPs library of NRSA, and this is one area where you can see at different spatial resolution what are the residuals or RMSE which you see for one set of the data set. So, at 30 meter resolution, this is what these are the values which you are getting, almost you are getting, so you are underestimating the height value, and whereas in case of 90 meter resolution you are again getting values, some are varying for different. So, since the resolution has changed, and therefore these RMSE values have also changed for with respect to different GCPs as well. So, this is one way. One example is here, that RMSE of Cartosat DEM, which is this one, and RMSE is this is 3.4, and whereas in this case it is 3.44 respectively, and linear error is 4.7. Another example of Dharamsala, which is a hilly terrain, and what you are seeing is again same comparison, Cartosat DEM 30 meter, Cartosat 90 meter, and this is what you see the error. Now, as I have been mentioning, that in hilly regions you may get altogether different values, and here what we see that this is the value in 30 meter RMSE is 4.72, whereas here it is 4.79. So, it's generally it is larger in of a hilly terrain. One more example of Rajasthan, not as rugged as Dharamsala, and these corresponding checkpoints are also there. So, this is the difference accuracy of Cartosat DEM and aerial DEM which have been derived, and again RMSE 30 meter resolution and 90 meter resolution 4.7, 5 points. So, coarser the resolution, the error component may be higher, RMSE may be higher. If a digital elevation model of a hilly terrain, again RMS error may be higher. So that has to be kept in mind. So this brings to the end of this assessment of the quality of a DM, and there are various methods which we have discussed in this one, and depending on the area on which you are working, depending on what is the source of digital elevation model, and depending on the spatial resolution of a digital elevation model, one should try to first assess the quality and then later employ to drive various products using that particular digital elevation model. So this brings to the end of this presentation. Thank you very much.